So let me read this to you guys again. It says the car on a circular track accelerates from rest. And the car experiences, here are your options, only angular acceleration, option 2, only centripetal acceleration, and then option 3, both angular and centripetal acceleration. So let's draw a picture of that. So I've got a circular track, and I've got my car. This is my car. Now, its original velocity is 0. Okay, and we could also consider that an angular speed of 0. And so it starts from rest. And then it speeds up, and it goes around the track. And so what they want to know for car A is, what does it experience? Does it experience only, let me write it in the same order of the book, angular acceleration? Okay, so that's option number 1. Option number 2, only centripetal acceleration? Both. So let's talk about angular acceleration and centripetal acceleration. Angular acceleration is our angular velocity, right? Our angular velocity or our angular speed is based on the angle changing. We can accelerate that. So when we talk about angular, here's the center of the circle. Our angular acceleration goes this way. Okay? And our centripetal acceleration goes towards the center of the circle. If it's on a circular path, does it experience 1, only angular velocity? Option 2, only centripetal acceleration? Or both? What do you guys think? All in favor of option number 1, only angular acceleration, raise your hand. All in favor of option number 2, only centripetal acceleration, raise your hand. And all in favor of both, raise your hands. Okay, good. It is both, right? It's both. In order for it to remain on the circular path, it has to have centripetal acceleration, and the angular acceleration is true because our initial angular speed is 0, and then it increases, right? So there's a change in angular velocity, therefore there's a change that changes the angular acceleration. Does that make sense? Now here's part B of the question. If the radius of the track is 0.3 kilometers, so we're gonna say that the radius is equal to 0.3 kilometers, and the magnitude of the angular acceleration is 0.45 radians per second squared, right? So we're going to say that the angular acceleration is 4.5, and it was times 10 to the negative 3. Okay? How long does it take the car to go around the track one time? So the question is, this is the radius, this is the angular acceleration. It starts from rest. How long does it take for this car to make one revolution? Okay? How much, when they say how long, they mean how much time to make one revolution. Okay? So what are we solving for? Solving for time, right? So we're solving for time. So now I've listed a bunch of stuff here. This is the initial angular momentum. So now how do I use all that information to solve for time? Well, wait, it says a half a lap, not one full lap. Wait, let me read this. This is how long does it take to make one full lap around? Oh, that's part C. I'm getting ahead of myself. All right, so how do I do that? I want an equation that gives me I want an equation that gives me time, that involves acceleration. So let's look on page, Mr. Adams already has his notes. I know how to do this. I'm pretending to be a student at home trying to do my homework. Okay? So what I would do is if I were you guys and I went home and I tried to do my homework, the first thing I would do is I would look at, on page 256, I'd look at those equations on page 256. All right? And what I would look for is I would look for something that involves most of the variables that I have listed. And then I'd have to figure out one that has time in it, obviously, because that's what I'm solving for. So, among all those equations, which ones have time? Well, I'm going to write them on the board, okay? So let's write them on the board. We'll pick one. Okay, there's a bunch of them, but I'm only write the ones that have time down. Now, sometimes this works, sometimes it doesn't, but you got to start somewhere. So if one of them is that my final angular velocity is equal to my initial angular velocity plus the acceleration times time. That might work. And the other one is my final theta is equal to my initial theta plus my initial angular velocity times time plus 1/2 times the acceleration times time squared. And that's it with time. Now, do I know my final velocity? Let's look at what we know. Do we know the final velocity? Not really. Let's write it down. Final angular velocity, don't really know. All right, what about theta? You know, if I subtract theta, the initial theta from both sides, I get theta final minus theta initial equals the initial angular velocity times time plus 1/2 times the acceleration times time squared. Isn't this the change in theta? I like to look at it that way. Okay. Well, do I know the change in theta? Well, what was my initial theta? How many radians did I move when the car first started? Right? The car started here. Isn't that theta equals 0 radians? Right? That's where I started. And then as I rotated around, how many degrees or radians did I rotate around? 360, but we want it in radians, so what's 360 in radians? 2 pi. Hey, do I know that? Apparently I do. Apparently you do too, right? So if I look at these equations, which one might work better? Uh-oh, where'd they go? Oh, I lost them all. Which one might work better? Probably this one, right? That one will probably work. So how would I do that? Well, what I could do is I could probably say that delta theta is equal to my initial angular speed or velocity, however you want to say it, plus 1/2 times the constant acceleration times time squared. And I pretty much know all these. What was my initial velocity, my angular velocity? And I always say velocity, but it's actually speed. It's a bad habit. I try to make the connection between the kinematic and the circular motion. But it's actually a speed, right? So what was the initial angular speed? How fast was the car going when it started? 0. So what happens here? Yeah, 0 times t is 0. So now my equation is delta, because that's 0, everything's 0, is 1/2 times the acceleration times t squared, the angular acceleration. Do we know the angular acceleration? Yeah. 4.5 times 10 to the negative 3 radians per second squared, right? Times t squared. Oh, hey, you know what? We also know delta theta, which is 2 pi. So I've got all this stuff here. 4.5 times 10 to the negative 3 radians per second squared times t squared. So what do you think I need to do? Can we solve this? Got a bunch of numbers and the variable t. So the first thing I'll probably do is let's get rid of this 1/2. How do I get rid of the 1/2 here? Multiply both sides by 2, so that gives me 4 pi is equal to 4.5 times 10 to the negative 3 radians second squared, right? Is that right? Times t squared. What's the next thing I need to do, guys? Divide by this stuff, right? 4.5 times 10 to the negative 3 radians per second squared, right? And then whatever I do on that side, I got to do here too. Now on your calculator, you could do it like this. Okay? Now with the radians, what happens with the radians? Isn't this in radians? So if I wanted to be technical, it's technically 4 pi radians, right? And so when I divide by this radians per second squared, when you divide by a fraction, what do? Multiply by the reciprocal. So this kind of goes away and becomes second squared over radians on the top. Now what happens with the radians? This radians cancels with that radians. So whatever my number is, I'm going to end up with that number. Second squared is my unit of time. So now to get the number, I'm going to fire up my calculator, and I'm going to say 4 pi divided by 4.5 e to the negative 3. Okay? So let's do it. 4 times pi, whoops. This is really frustrating. That's 4 pi. We're going to divide it by 4.5 negative 3. So I get 2,000. Well, I get that number. Okay? So we need to write that down. So that whole thing was 2,000, what was it? Let's write that down. It's 2,000, let's do 0.53. So 2792.53. 279, was it 2.53? And that's equal to t squared. Well, what do I need to do? I want time, not time squared. So what do? Square root of both sides, right? Square root of this side. What happens to my second squared when I take the square root? Seconds. And so when I take the square root of all that stuff, I get about 53, right? So my answer should be about 53 seconds. And you say, well, I don't know, Mr. Adams, prove it to me. Okay, fine. Second, oh. If I want to do it on the calculator, why is that so goofy? Second. So it's 52.8, but when you round it up, you might as well just say 53 seconds, right? Okay. Now part A says half that. Now would you just take 53 and divide it by 2? No. What would you do differently to find part C? To find part C, part C wants to know, well, that's cool. What about 1/2 of a lap? What would the time be then? Well, you do the exact same thing, but your delta theta would change. So what would delta theta be? Instead of 2 pi, it would just be pi. So it would be pi is equal to, right? And then it would be 1/2 times the 4.5 times 10 to the negative 3, right? Times squared. And then you would solve that one. And if you were to solve that one, what would your answer be? Oh, actually, wait, they asked a different question, actually. Maybe we should crank through it. So it says, what is the total vector acceleration of a car when it is completed half a lap? Oh, wrong question. At a half a lap, it wants to know what is, let me read it out loud and then we'll solve it. What is the total vector acceleration of the car when it is completed a half a lap? What is the total vector acceleration of the car when it has completed half of a lap? Well, that's really just the final angular velocity. So to do that one, it's a little more complicated. So basically after a half a lap, so you've got this circle, right? Here's your car, and it does one full lap. First thing that we want to do is we want to calculate what is its angular velocity. Or speed, I should say, its angular speed. Now, we were going to use a different equation, which is going to be the angular speed, right, squared. My whiteboard's acting goofy again today. It's not so. My smart board isn't so smart. My final angular velocity squared is equal to the initial velocity squared plus 2 times the angular acceleration and then of theta. All right. So now this. Our initial velocity or speed, our initial angular speed was 0, plus 2 times 4.5 times 10 to the negative 3, and then a half a lap is just pi, right? So we get our final velocity, our final angular velocity at 1/2 a lap is all this stuff. And if you plug that in a calculator, you get 0.0283 radians per second, okay? It's actually radians squared, seconds squared, all right? And then if you take the square root of both sides, you get your final angular speed is 0.168 radians per second, okay? And you say, well, what does that have to do with the vector, right? What is the vector acceleration? Well, the vector acceleration and the tangential acceleration have a relationship, right? And so this one's kind of complicated, but it may not. Let me just go through the math and then I'll try to explain it. We have centripetal acceleration, right? Because it experiences both, and that's equal to the radius times the velocity, the final velocity squared. Okay. And then we said it also experiences a tangential acceleration, right? Which is equal to the radius times the angular acceleration. Okay, and we'll crank through that in a second. So maybe I will go and try to explain what's going on, and then we'll bounce back and forth. We said in part A that it experiences both types of acceleration. Now the total vector acceleration has to do with how the car moves. Okay, how it rotates around in the amount of time that it rotates. All right. And you would use polar coordinates. Well, how do we find those polar coordinates? Well, we've got to first find the magnitudes of the centripetal acceleration and the tangential acceleration. And these formulas are on page 256 and 257, if you guys are curious. So then what was the radius? Well, the radius we said was 0.3 kilometers, right? And then we just solved for the angular velocity, which is 0.168 radians per second. And so, and that was all radians per second. And then this whole thing needs to be squared. And so this right here, let me move this down a little bit. This whole thing right here, this centripetal acceleration, if you multiply all this on the calculator, is 8.5 meters per second. Now what that means is that there's a force being applied on this car to keep it in the circular path, and that centripetal acceleration is pushing in at 8 meters per second, 8.5 meters per second towards the center of the circle. Does that make sense? So the path of the car is the resultant vector of these two accelerations, where one acceleration is constantly changing. Actually, both of them are, when you think about it from a vector perspective. So when we come back now, we're going to do the exact same thing, but now what we want to do is we want to find that with regards to the tangential. Well, the tangential is going to be 0.3 kilometers times this 4.5 times 10 to the negative 3, and that number is going to be 1.4. Whoops, not 1.5, 1.4 meters per second squared. So this is meters per second squared, 1.4 meters per second squared. Now what that means is I've got this car. Okay? This is my car. And it's going to go on a circular path. Now in order to go on the circular path, it's going to have an acceleration, centripetal acceleration, that has a magnitude of 8.5 meters per second squared. All right? And then it's also going to have a tangential acceleration, okay? And that tangential acceleration is 1.4 meters per second squared. Okay? The resultant vector of those two vectors is what they're asking for. Does that make sense? Okay, it's a little confusing when you do all the math, but so what is that? Well, the resultant vector, if I want to, I can label it like this. I could say that my acceleration vector is equal to, and since it's negative, we have to arbitrarily choose which way it's going, right? So at this point, it would be 8.5, and this one would be down this way, 8.5. Now, I don't care which way you choose to be positive or negative, right? But clearly one of them will be negative, and one of them will be positive. Now, the way your textbook chooses to do it is it chooses to say negative 8.5 meters per second squared. And then because that has to go towards, because that's going towards the center, it calls it r hat, right? And then plus the 1.45 meters per second squared, t hat. and you just leave it like that.